Hi everyone, and welcome back to my channel. Today I'm going to discuss the process of an action potential. An action potential is the process of conveying an electrical signal across a neuron or muscle cell. It is characterized by a sudden rise and subsequent fall in membrane potential. Now if you're a med student, there's no doubt you would have seen this graph. Basically, it shows a change in voltage during an action potential. Membrane potentials are predominantly determined by the concentration gradient of sodium and potassium ions. So let's jump straight into it. The resting membrane potential is the voltage of the cell at rest. Typically, the resting potential sits at minus 70 millivolts, meaning the inside of the cell is more negative than the outside of the cell. Due to the voltage difference, the cell is said to be polarized. At rest, there is a higher concentration of sodium ions in the extracellular space in comparison to potassium ions. Firstly, to start an action potential, the cells need to be stimulated. In this case, assume this cell is an excitatory glutamate neuron. When the glutamate binds to its receptor, it causes mechanical gated sodium channels to open, allowing sodium ions to enter the cell. Remember, sodium ions have a positive charge, making regions of the cell more positive, in other words, depolarized. The more sodium that enters the cell, the more the cell depolarizes. If it reaches the threshold of minus 55 millivolts, indicated here, an action potential will occur. As the cell becomes depolarized, in other words, more positive, neighboring voltage-gated sodium channels are activated, causing a sodium influx, which enables the action potential to propagate across the cell. Basically, it's an all or nothing rule. If there is insufficient stimulation, action potential will not occur. We should note, the higher the intensity of the stimulus, the more frequently an action potential will fire. Now, straight after a peak of positive 40 millivolts, the cell goes through a phase called repolarization, indicated by this sudden drop in the membrane potential. At the peak, voltage-gated potassium channels become activated and potassium ions are transported into the extracellular space. Potassium ions have a positive charge, therefore the transportation causes the cell to become more negative again. Further to that, sodium channels become inactivated, ceasing the sodium movement across the membrane. In fact, there is so much potassium leaving the cell that it becomes more negative than the resting membrane potential, to approximately minus 90 millivolt. This is known as hyperpolarization. To restore the cell at resting membrane potential, the sodium-potassium pump becomes activated. This structure pushes 3 sodium ions out of the cell for every 2 potassium ions entering the cell, of course with the help of ATP energy molecules. Just before the cell becomes hyperpolarized, the cell enters a relative refractory period, meaning a larger stimulus is required for the next action potential. Another period of significance is the absolute refractory period, meaning the cell cannot be stimulated during this time. That's all for today, folks. Thank you.